Welcome to part 2 of the parametric equations lesson for Calc 2. As promised, this time we're going to do another example, and then we're going to go a little step further with this example, and we're going to see if we can transform the parametric version of the equation back into what I call a implicit version of the equation. Implicit is definitely a word that I made up. If you look it up, it's probably not in any dictionaries yet. When I'm rich and famous, it'll be everywhere. For now, it's just a word I made up to describe like regular functions, like x equals some function of y, or y equals some function of x, without the t's involved. So let's just get started on an example. I want y to equal t cubed minus 2t. And I want x to equal, x can be 3t. We'll do this. No, x is 3t. That's good. This will be good. So, as usual, I'm going to start with a table of values. I need a row for the t values I'm going to use. I'm only going to go with 5 this time. Let's go with -2, -1, 0, 1, and 2. And I need some x values. The x values corresponding to these will just be -6, -3, 0, positive 3, and positive 6. And I need some y values. Y values here are going to look like -8 plus 4 is -4. -1 plus 2 is +1. This one will be 0. This will be 1 minus 2. And I plug in t equals 1 for this. You get 1 minus 2 gives me -1. And when I plug in t equals 2, I'll have 8 minus 4 is 4. So these will be the ordered pairs that I need to put onto a graph. So I'm going to come up here and graph that real quick. Kind of a small graph. I want to leave some room to do other stuff over here. Again, I'm going to try to put these points on in order. Partly because without the vertical line test, if you just put a bunch of dots on a board, it's not immediately clear which dots should connect to which other dots. Like for the last example we did in the other video, we had dots in this sort of U-shaped pattern. And like we could have just kind of connected them like a zigzag, right? Like it wouldn't have been correct, but like it kind of looks like you should zigzag them. This is why putting them down in order is important. It's also going to help us with the orientation of the curve, whether we know it's moving like to the left or to the right or vaguely up, vaguely down. So graphing these points in order is very important. So I'm going to start with -6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. -6, -4 is down here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay. -6, -4, we'll start there. -3, +1 is up here. 0, 0 is right in the middle. +3, -1 is right here. And then +6, +4 is up here. So it looks like I have something doing some kind of wiggle through there. Probably goes down there too. Oh, I'm not going to draw that arrow though, because I want to preserve the orientation of this graph as something that moves from left to right, because it wiggles vaguely upward. So this is what the graph of this looks like. Now the next goal is to see if we can create a implicit formula for this function. That is, instead of having x and y defined separately in terms of t, I'm going to see if I can create, as my goal, something that just looks like y equals some function of x. This is where I want to end up. To get there, for this particular problem, I'm going to use a technique called elimination of the parameter, which means I'm going to start with this x equals 3t. I'm going to mess with it a little bit. I'm going to say t equals x over 3. And if this is what t equals, I should be able to plug this directly into these t values to create a function for y. So let's see what that looks like. Y equals, used to be t cubed, now it's going to be x over 3 quantity cubed. Used to be 2t, now it's going to be 2 times x over 3. So this is, for now, an unsimplified version of the implicit form of this function. I'm going to simplify it a little bit. I can probably cube this pretty easily. Y equals x cubed over 27 minus 2/3 x. And there it is. If you want y as an explicit function of x, it's x cubed over 27 minus 2/3 x, and it still looks like this. If you graph just this, you'll get the same shape without the orientation. Regular explicit x equals some function of, or y equals some function of x functions don't have an orientation. They just have ordered pairs. This has an orientation because it's coming from a parameter t, and the parameter, as the parameter increases, you move through these points in a direction. So that's the implicit example. I want to go back to the first example and see what it looks like when we try to do this implicit stuff to that problem. Okay, so the first example was y equals 4t minus 1 and x equals 2t squared. This was what we started with. And my goal for right now is to eliminate the variable so that I have a function of just x's and y's. And there's sort of two ways we can do that. The first way is going to involve using this one here. So I'm going to take this y equals 4t minus 1 and turn that into y plus 1 equals 4t. And then I can turn that into t equals y plus 1 over 4. Just using some algebra on that until I get it solved for t. Now we can plug that in here for t squared and see what x looks like. And if I do that, I will get x equals 2 times the quantity y plus 1 over 4 squared. So this is sort of the implicit version. There's no more t's involved. It's not simplified. I can simplify it though. First thing I'll do is square the 4 on the bottom and get rid of that so that it's not mucking up the rest of this algebra. So 4 squared would be a 16 on the bottom, so this is 2/16. I'll call that 1/8 y plus 1 squared. And then I can square y plus 1. I'll have 1/8 times the quantity y squared plus 2y plus 1. And then if you're very enthusiastic, you can distribute that 1/8. And you would get x equals 1/8 y squared plus 1/4 y plus 1/8. So this is a simplified implicit function with just x's and y's, no parameter, no t. The parameter has been eliminated. Some of you may be wondering, isn't this backwards? X is a function of y? That's not how this works. Y is supposed to be a function of x. And I would like to remind those of you who are thinking that this particular parabola was sideways. We can't have a really nice, convenient y equals some function of x because the graph didn't pass the vertical line test. So you can sort of flip your inputs and outputs here and say that x is some function of y. Like, it's sort of like what we did when we were doing volumes of rotation. And you had these like square root functions and you had to flip. Functions were defined as like x is a function of y or y is a function of x, and you sometimes had to flip that so that your integral was using the correct variables. It's like this. We could describe x as a function of y in this case. Or we could try to eliminate the variable using x here, and some weirdness would happen. It's worth looking at. If I did it that way, I would get something like, trying to solve this guy would give me x over 2 equals t squared, and then t equals plus or minus square root of x over 2. So here's where we're getting that vertical line test failure sort of business. If we try to plug this in here for t, we're going to end up with two functions. We're going to have a y equals the positive square root function of this, and we're going to have a y equals the negative square root function of this. And that's what's going to give us the, if we try to create an explicit function for y as a function of x, that'll give us the two branches, the positive square root and the negative square root. And it would look like y equals positive 4 square roots x over 2 minus 1, or negative 4 square roots of x over 2 minus 1. For this particular example, this two separate versions of the problem thing is why we are not really going to solve this explicitly for y. So don't do this. Best we can do for this one, let's drop our marker. Best we can do for this one is x as a function of y. Again, because our parabola is sideways. Some of you may remember from Calc 1, we talked about a section called implicit differentiation. And in that section, we talked about the difference between an explicit and an implicit. Oh, this marker does not erase. Wish I had known that 5 minutes ago. Oh, it's so nasty. Ooh. Get rid of red, please. Okay. This marker's going away. So, in Calc 1 we talked about the difference between an explicit and an implicit function. Explicit usually means solved for y. Sometimes in this section you're going to have to flip which variable is which. So sometimes you'll end up with something that's solved for x. An implicit means that stuff was still happening to x or y, not solved. So, a lot of these functions, if you start with a parametric function and you eliminate a variable and you transform it into a function of just x or y, a lot of times you can get it into an explicit form, like we did here. Here we have x is an explicit function of y. The one we started with was y as an explicit function of x, our little cubic guy, x cubed over 27. That example we got into a form that was explicit, y is a function of x. That's not going to work with all the parametric functions that we deal with in this section. Some of the functions we deal with are going to be weird shapes that you can't do with normal x and y functions, and so we're going to have to leave those implicit. We'll leave, stuff is going to be happening to x's and y's, and we'll just leave it that way, and that's fine. But this idea that sometimes it'll be explicit and sometimes it'll be implicit, this is what has led me to call this type of function implicit. So, that's where the word implicit came from. I made it up based on these two words. It's not a real word, but it works, and I like it. So, this is the goal of this section. We're going to make tables of values for parametric equations. We're going to graph them with the orientation in mind, and then we're going to create implicit versions of those functions. The homework is going to say eliminate the parameter. I say make it implicit. That's the third thing. And they're going to get more complex than this, which I will start to talk about in part 3.